Good day, ladies and gentlemen. We are welcome to our course. The first part of the lecture, the title of the course is Reliability and Maintainability of Electrical and Electronics Components, and the course code is Ele5203. My name is Engineer Kia Abu Bilal, PhD, and I'm from Department of Electrical and Computer Engineering of Ahmad Bello University, Zaria. Before we go into the course, there are some important points I would like to call up the attention of the students to. The first thing is I want you to always ask me questions. By asking questions, you understand better. And I'm not saying that I have answer to everything. I can have answers to some instantly, I answer them. Those that I don't have, I'll go and find the answers and bring them in our next meeting. And also, I encourage the student not to pay much attention to getting A in the course. No, try to get the knowledge first. Then the next target should be to get a good result, which is that A or anything like that. The references I would like to give to the students are given here. I have 3 books, but the first one, The Fundamentals of Reliability and Testing Methods, is very, very important. So the student should try to maybe consult these materials. The next item is the course content, and you can see here we have 6 items. Therefore, we can call this one 6-point agenda. And it starts by introduction. It goes to elementary reliability theory, applications to electrical and electronics components, then the test characteristics of these components, different types of faults, and the methods of designing for higher reliability. So let us start from the introduction. You know, as an engineer, you are expected to be able to design systems, but your ability to design is rated by the level of reliability of that system you've designed. If it is very reliable, then you are a very good engineer. If it is not reliable, the opposite is the case. Look at the materials, the items, the product we buy from China. We always categorize them as products of very low reliability, very faulty. Therefore, Chinese engineers, as far as we are concerned, they are not good because their systems fail frequently. And one thing we need to know is that the issue of fault or failure is something inevitable. You can never have a system that will work forever without failing. No, it will fail. So another parameter we use for rating the standard of an engineer is the possibility of repairing that system when it experiences a failure. Is it easily repairable? If yes, then the design engineer is categorized as a good one. We go to the different definitions in this our introductory aspect. The first thing is we try to define the term reliability. What is reliability? The reliability is defined as a characteristic, that is a property, a feature of an item, of an equipment, of a product, of a system, which is expressed as what? A probability that that system, that item will perform its required function. This is one key statement. Under stated condition, second key statement, for a stated period of time. This is the key definition or the key point number 3. What we are saying here is that we can have different types of definitions of reliability, but these keywords or these key phrases, performing the required function under stated condition for a given period of time, they are always emphasized. So therefore, the reliability of any product is what is the probability that it will do the required function under stated condition for a given period of time. Now, one important thing we need to understand from this definition, we said it is expressed as a probability, and you know the probability has values from what? 0 to 1. Meaning, if the reliability of a system is equal to 1, it means that system is perfect. It will never be faulty, and you know that perfection is not possible. And on the other hand, if the reliability is found to be 0, it means the system is not working completely, and this definitely happens. There are some systems that will not work. Therefore, at that time, at that condition, their reliability is equal to 0. And any value we get between 1 and 0 it is showing the relative level of the reliability. If it is like 0.7, you see it is approaching 1, therefore it is highly reliable. If it is approaching 0, maybe 0.2, 0.3, all of them we call it low reliable. So there is another important thing we need to know or to highlight from that our definition. We said it is the probability to perform required function under stated condition, and we know the reliability now of an electric component must be subject to what kind of stress from vibration, that's mechanical stress, is that system subjected to, what kind of voltage fluctuation is it subjected to, what kind of frequency fluctuation, current. So it means whenever you're trying to determine the reliability of system, you have to look at all these conditions. But if you just do it without giving attention to this point, your value you have obtained will not have any real meaning. So we now come and define what is a system. System is defined as a complex whole set of connected parts or components with functionality related properties in such a way that the combination of all these components put together will perform a particular task. Therefore, a system is combination of different components. Now, what is the component? The component is defined as a constituent, that is a part or an element belonging to a system that is an individual element this time around. So if you look at these two, system comprises of many components, whereas component is a standalone device, meaning whenever you are trying to find the reliability of a system, the procedure will be harder, will be more difficult than when trying to find the reliability of a single component. Now the definition continues, and here we are going to define some terms related to the reliability. The first one is reliability assessment. What is reliability assessment? This reliability assessment is just a procedure of estimation of that probability of a system to perform the function under stated conditions and within a given period of time. So the process of estimating the reliability is what we call the reliability assessment. The second term is reliability evaluation, and this term stands for the determination of the frequency of the failure of a system or a failure of a component within a given time. The process of determining the rate of failure is what we call the reliability evaluation. Now the third item is reliability analysis, and this is just a method of engineering analysis in such a way that we will determine what should be the best way to improve the reliability of a system. Is it by introducing extra components that should be standby in that system, what we call redundant systems, or by upgrading the original system and make it more qualitative? So the procedure of assessing how to improve the reliability is what we call reliability assessment. Now there are different approaches, different methods of reliability assessment and evaluation techniques. First, there is reliability assessment that has to do with hardware components, and there is what has to do with software components. And it is very important to note that if we are dealing with electric power supply system, there are two key reliability items that we look at. The first thing is adequacy. That is the ability of the system to supply the aggregate, that is the total amount of electrical demand. We use it to assess how reliable is the system. And the second is the security issue, that is the ability of the system to withstand some unexpected situations like sudden increase in voltages due to short circuit, like open circuit, like other environmental parameters that can affect it. So its ability to withstand it is another feature that we use for assessing the reliability of power supply system. Now we continue with our definition. We are now going to see the definition of maintainability. Maintainability is also a probability that a unit or a system will be restored to normal operation, that is after it failed, the probability of restoring it back to the normal operation with the required level of efficiency within a given period of time is what we call the reliability. And of course, the process of restoring it back is done by what we call maintenance actions. That is, you maintain it in order to bring it back to normal operation. So that probability is what we call the maintainability of the system. Since we have this word probability, it means the probability values range from what, 0 and 1, and sometimes we express them in percentage. What goals do we want to achieve by carrying out the analysis of maintainability? The first thing is, we want every maintainability process to be of least time. That is, it should take a very short time for the maintenance action to be completed, and also the least cost, that's the amount of money in aggregate that should be spent for restoring the system back, should be as small as possible. And it also have a goal of achieving minimum expenditure for supporting resources, that is individual items that made of total cost of maintenance. They include the manpower, the spare parts, the tools, and the test equipment. Now we go to the definition of another term, that is the availability. The availability of a system is also defined as the probability of that system to operate satisfactorily at any point in time when it is used under stated conditions. That is, the probability for that system to work normally with good efficiency when operated under given conditions. That probability is what we call the availability. And that time we made mention in the definition, it includes two components. There is operating time, when the machine or device is operating, and there is what we call active repair time, the time taken for actual maintenance duty. This availability in engineering has its roots from the reliability and what, maintainability, because whenever a system is reliable and it is maintainable, definitely we expect it to be available at any point in time. We continue with our definition. We come to another term, they call it dependability, and this is the collective term that is used to describe the level of availability. That's the level of possibility for the machine to be available to work at a particular time. So this dependability is availability performance, and it influencing factors as we have seen. What determines availability is what, the reliability of the system and what, its maintainability. Now another term we need to define here is what they call failure. And the failure of any system or any item is the termination of the ability of that item to perform its required function. Whenever a system cannot perform its required function adequately, we can say it experiences failure. And every item has its own operating or operational characteristics. So any deviation, any change from those normal characteristics in the operating condition of that system, we consider it as a fault. And therefore a fault is what, a state of failure. An item is now considered to have failed if it experiences one of the three items here. The first one, when it becomes completely inoperative, that is, if it cannot work completely, then we say the system has failed. Another condition is when it cannot perform the actual specified function. For instance, let's say we have an electric motor designed to rotate at 1000 RPM, but instead of that it reduced to only 400 RPM, revolution per minute. Though it is working, but it is not given the required performance, therefore it is said to have experienced failure. And the last condition under which we say a system has failed, when it is unsafe to be used. For instance, if you have an electric pressing iron, but if you touch it, it shocks. It is very dangerous for you to use it for pressing your clothes, and therefore we say that pressing iron has failed. The failure is also categorized into three. We have what we call primary, secondary, and we have command failure. What is the primary failure? We define it as the failure caused by natural aging. That is, as the machine is being used for a very long time, it is becoming old and old. So those failures that will be happening when it is in operation, we call them primary failures. And whenever this kind of failure occurs, there is need of repair action. We have to repair the machine in order to return it back to the normal operating state. The second one is called secondary failure, and it is any kind of failure that is caused by excessive stress, that is to subject it to a very high condition above what it is designed for. For instance, very high temperature, very high mechanical vibration, very high electric current or voltage. All these can cause what we call secondary failure. And this failure, whenever it happens, there is need of repair action also to bring back our item or system back to operation. The last one, they call it command fault. And this kind of fault is a fault that is caused by improper control signal. That is, if you send a wrong command for a system, for instance, let's say you have a code lock that you use for closing your door or closing yourself, and maybe the number is 1435. So if you want to open it and you put 2, 3, 5, 6 different from what you have, it will not open. So it is not performing the function of opening. Why? Because you have given it a wrong command. So this kind of commands, failure, when it happens, there is no need of repair action. All you need to do is to send the correct signal for it to start working. So we have seen that it is inevitable for failure to occur. What are the main causes for occurrence of the failure? The first one is the design inherently incapable. That is, if there are some errors from the designer, that the design has some inherent errors, there is tendency of failure. Another thing is overstress in some ways. Too much temperature, too much voltage, or anything higher than its ability. And the next one is what we call wear out failure. This is a kind of failure that happens as a result of aging. When the machine is becoming older and older, its parts are becoming weak, and therefore it will be experiencing more frequent failures. Another reason that can cause failure is variation of supply. That is, if you are to power your system with, let's say, 12 volts DC, but the voltage keep on changing to 14, 16, up to 24, that is variation of voltage, and it can cause failure. And another factor that causes failure is wrong specification. That is, if a designer designed his system to operate at 1 amp maximum current, but instead of writing 1 amp, maybe he mistakenly in the manual puts 2 amps. If you subject it to that high current, it can malfunction, and there is misuse failure. This is the reason that causes failure when somebody that's supposed to operate an item or a machine did not operate it accordingly. And we have environments in such a way that if a designed item is used in a different environment from where it is designed for, we are expecting it to be failing. So what are the objectives of learning reliability engineering? The objective number one is to apply the knowledge of engineering to prevent, if possible, but the prevention of failures is not possible, so to reduce the frequency of the failures as much as possible, to reduce the number of failures. Another objective is to identify and correct causes of failure that occur, to understand what causes the failure. The moment you know them, you can provide a means of handling them. And another objective is to determine ways of coping with the failures when they occur. Since we said it is inevitable for failure to occur, so what are the ways we can withstand them even when they happen? This is one of the objectives of learning reliability engineering. Item number 4 is to apply the methods of estimating the likely probability of what the new design. That is, if you design new system before you even produce it and start selling, your knowledge of reliability will help you to identify what are the possible items that can cause failure to the system. So before you produce it, you correct those things so that it will be durable in operation. And we also learn this in order to determine the potential risks. What are the possible dangers that the failures will cause to the people operating the machines or using the machines? If you know them, it will give you ability to design for what, avoiding them. And finally, another objective for learning reliability engineering is to enhance environmental protection. Yes, whenever you're using systems, machines that are very reliable, there is every tendency they will produce very minimal amount of what, pollution to the environment. Therefore, they are protecting the environment from the effect of pollution. So the next thing is reliability statement in product specification. When a manufacturer produces any goods, ideally he produces a manual that will be sent together with the designed product to the customer so that they will use them in order to know some information about the product they bought. So the issue of reliability has to be included in those manuals. And the first item that is expected in this respect is to make sure that any failure related information of that product are included in that manual. All the methods, all the possibilities of failure should be included. Another item, which is number 2, full description of the environment in which that product should be stored, in which that product should be transported, in which it should be operated and maintained should be stated, so that it will be stored properly, transported properly, operated properly, and maintained properly for it to have higher reliability. Finally, there is need of given statement of the reliability requirement. That is, what the user need to do in order to enhance the reliability of the system. Another thing we are going to look at is, why is reliability important? In other words, what are the importance of what? The reliability. First, it improves safety. Whenever system is reliable, it is much likely to operate perfectly without any failure, and that improves the safety of the machine and the users. And it helps competitiveness. If somebody brought, let's say, televisions, one is made in China and the other one is made in Japan, and they are free of charge, you should take them. Which one do you take? Definitely you take that of what? Japan, because we know the reliability of their products are very high. Therefore, it helps the competitiveness of a company. It also improves the profit margin. Yes, the more the people buy your products, the more the profits you get. And also it minimizes the cost of repairing the components and maintenance of the component. Yes, the lower the number of what failure, the smaller the amount of money you should spend in repairing it or in maintaining it. Therefore, it reduces the cost. Item number 5, among the importance of what reliability is, it brings about lack of reliability, brings about delay further of the supply chain. If your company produces products that are not reliable, even if you produce them, before you send them to it will take you a long time trying to investigate because they are not reliable. Or even if you start selling, there is what they call callback. When the customers say they are faulty, you have to bring them back. Therefore, the rate at which you are supplying them is reducing. And finally, it affects the reputation of the company. Chinese products, they have bad reputation because of low reliability. Japanese, America, UK products, they have good reliability because they have products which are very reliable. Now we go to the second item, meaning what we have done so far is on the introductory aspects. Now we are going to start the elementary theories of reliability, and we start by defining some terminologies that are related to the reliability of any item. The first one is called mean time between failures, that is MTBF. And what is this time? This is used for items which are repairable. There are some items, once they fail, you throw them away because you cannot repair them. So the mean time between failure is a terminology used if we are dealing with components that if they fail, you can repair them and continue using them. And this value is computed based on two methods. The first method is called replacement method, and the second one is called non-replacement method. What are these two methods? The replacement method first. And this replacement method is a method in which the mean time between failure, which is given by small m, of a system is measured by testing it for a total period of Tn. That is the component you test it for a period of Tn, where T0 is the time where we started doing the what? Testing. And this Tn is the last time where end peak failures had happened. Misali, for instance, sorry, I use Hausa, but you said in your class it is allowed to use Hausa. For instance, if you have a system, you start using it, it failed, you repair it, you start using it again, it failed, you repair it. So if n failures happen, the total time is this our Tn. And this T, which is the total time, is given by this formula, that is m is equal to T over n, where T is the total time, n is the number of failures. And you can see that it is equal to T1 minus T0, that is the time before the first failure occurred. T2 minus T1 is the time before the second failure, and T3 minus T2 like that up to Tn minus 1 should give me different times when the machine is operating, that is times between the failure. And if you expand this bracket, you see that this T1 will be subtracted by this T1, they will go. And if you put another bracket here, you see T2 will be subtracted, so all of them will be eliminated. The only thing that will be left is what? Tn, which is the last time, and T0, which is the beginning time. So if this T0, the beginning time, is 0, my m, mean time between failure, is equal to Tn all over n, where Tn is the time when the end failure has occurred, and my n is the number of what? Failures. In order to understand this, let us start looking at worked example number 1. It says a series of continuous tests were carried out on an electronic system, and the faults discovered were repaired immediately they occurred, and the machine continued to work. When another failure occurred, it is repaired and the machine continued to work. And these are the values we have. At the time we have 0 failure, that is the starting time, my time is equal to 0 naught. That whatever we have here should be multiplied by 10 square, which is 100. When the first failure happens, it happens at 2 times 100, which is 200 hours. It is repaired and it continues to work. The next failure at 400, the next failure at 800, the next failure at 1000, next at 1400, and the last failure at 1500 hours. Now we are asked to calculate our mean time between the failure, and we know the mean time between the failure is equal to Tn minus T0 all over n. What is my Tn? Is T6, which is 15. T0 is 0 all over number of failures. You can count T1, T2, T3, all of them are 6 all over 6. So now I will have 15 minus 0, which is 15, times 100 is 1500 all over 6. It will give me 250 hours. The second method, which is non-replacement method, is a method where a large number of items are put together under test, and the observations are made for the possible failure at the beginning of the experiment and at the end of the experiment. We put large number of components, and each one we observe it to see what is the failure that can happen at the time we started the measurement, and what is the failure that can happen at the end. In other words, we are saying this method is limited to the useful lifetime, that is from the beginning to the first time where the failure happened, and that is what we call useful failure time or lifetime. The formula we use for estimating the mean time between failure for non-replacement method is given here. M is equal to test hours for failures, that is number of hours for those components that have failed, plus test hours for survivors, that's the number of hours for those components that didn't fail up at the end. and here is the total number of the component that have failed. The summation of these two times, we call it the total component test hours, and we call it survival hours. For us to understand this one easier, let us look at the following example. Worked example number 2 says, to determine the mean time between failure of certain components, 50 pieces of those components were tested for a period of 200 hours, and the times for the failure of each component are given in this table, and a sum total of 35 components survived. At the end of the day, they didn't fail, which means out of 50, if 35 survived, definitely 15 failed. And what we are asked to calculate is that we should calculate the total test hours before the failure, we should calculate the total test hours without the failure for the survivors, and we should calculate the total survival hours, and finally we should calculate the mean time between failure. Now if you look at this one, 6 components failed at the period of 100 hours, 5 at 140 hours, 4 at 175 hours. So the first thing I will do is to say, okay, the total time taken before those 15 component failed is given here. 6 times the number of hours, which is 100, plus 5 times 140 plus 4 times 175. So if you add everything, it will give you 2000 hours. This is the hours that has been taken for 15 components to fail. And if we go back, we are told that the test was carried out for a period of 200 hours and 35 components did not fail. Now the time for those components that did not fail should be 35 times 200, which will give me 7000 hours. My total time, which is called the total survival hours, is 2000 plus 7000, which is 9000. Finally, my mean time between failure, M, is equal to the total survival hours, which is 9000, all over total number of components that fail, which are 15 in number. So 9000 over 15 will give me 600 hours. That's the average time between one failure of the component and the next. One thing I want you to look at is this: the test was conducted for a period of only 200 hours, but the average time we have obtained is up to 600 hours, 3 times. Therefore, we use different method of reliability to conduct an estimate of a longer time within a very short time. If we understand this, the next thing is we look at another term. They call it the failure rate. The failure rate of any component is a way of expressing the mean time between failure of an item through this failure rate, and the failure rate is defined as what? The number of faults per unit time. How many failures do we have in a unit time? This failure rate is represented by lambda, and it is approximately constant in value. That's the value of failure rate for different component. It is somehow constant. For a resistor, it has its own, capacitor, transistor, all of them have their own, and they are expected to be what? Constant. So the mean time between failure is the reciprocal of this failure rate of any device, meaning M is 1 over lambda. We can say lambda is 1 over M also. And to understand this, we express this M in terms of what? Hours. And the failure rate is number of faults per hour. For instance, if the mean time between failure of a component is bound to be 4000, my failure rate, which is 1 over that, should be, if you say this over this, it will give you this. Let us use calculator and see. That is, if I say 1 divided by 4000, it will give me this. Now if I want to express it in percentage, I will multiply by 100, which is this. But if you look at what we have here, we express it as percentage of what? 1000 hours. So if I want to change this as a percentage of 1000 hours, I'll say times 1000, and if you do that, it will give you 25% of what? 1000 hours. So what are we saying? We express the failure rate as a percentage of 1000 hours. So another thing is defined as, or is called, mean time to failure. This mean time to failure is a terminology we use when assessing the reliability of components, devices which are not repairable. Those that the moment they fail, you just throw them away, like resistors, like capacitors, like bulbs. All of them, when they failed, there is no way of repairing them. Although these energy saving bulbs we have today, they can be repaired, but here I'm talking about filament lights. And the mean time to failure is defined as the average time an item will operate before it can fail. This mean time to failure is computed after testing the number of items n in a specified way, such as applying certain electrical signals, voltage, current, frequency, mechanical vibrations, certain heat, certain humidity conditions. When it is tested, now until all these components have failed, then if we assume T1 is for the time for the failure of the first item, T2 second item, T3 third item, up to Tn. So the observed mean time to failure is given as this formula. That is, mean time to failure is the summation of Ti minus T0 all over n, where I start from 1 to n. Now if we expand it, it will be T1 minus T0 plus T2 minus T0 plus T3 minus T0 up to the Tn minus T0 all over n, where n is the number of failures we have. Now the T0 is my starting time, which is the reference time, and T1 minus T0 is the period for the first failure, T2 minus T0 for the second failure up to the n. To understand this clearly, let us look at the worked example number 3, which said the live testing was conducted on 6 unrepairable electrical resistors. They are unrepairable. The results obtained are given in this table. We are asked to evaluate the mean time to failure of these resistors. At time 0, 0 failure; at time 4, 1 failure; another failure occurred at time 10, another failure at time 16, time 20, and time 25. And all these values are multiplied by 10 square, which is 100. Now, for me to find the mean time to failure, I will say T1 minus T0 plus T2 minus T0 up to T5 minus T0, because that's the last thing I have, all over n, and my n should be this failure 1 plus 1 plus 1 plus another 1, and here is 2. So I will say 4 minus 0 plus 10 minus 0 plus 16 minus 0 plus 20 minus 0 plus 23 minus 0 all over 1 plus 1 plus 1 plus 1 plus 2, which is 6. Finally, I got 96 all over 9, but you know it is multiplied by 100. So if you see 96 over this, should give you 16, and 16 times 100 will give you 1,600 hours, which is the average time to failure of these resistors. Now we are going to classify failure into different categories with respect to different conditions. The failure can be classified with respect to what causes the failure, with respect to the timing when the failure occurs, with respect to the degree of the failure. Is it severe, is it simple, and with combination of these 3 items we mentioned. Let us start with the first one. Classification of failure by causes. The failure is classified into misuse failure and inherent weakness failure with respect to what is the reason the failure happens. The misuse failure is a failure due to stresses above the stated limits of the item. Supposing you have a battery, you want to charge the battery, and the charging current recommended is 5 amp. Instead of putting 5 amp, you supply 20 amp to it. So if it fails, we can say this is failure due to misuse. And the failure which is due to inherent weakness in the device is a failure that happens due to weaknesses inbuilt in the materials when subjected to stresses within its specified limit without any overstress, but because it is inherently weak, it fails. This kind of failure, we call it inherent weakness. And what causes the inherent weakness is the failure in proper design. Now, classification of the failure by the timing, the time when it happens. we have what we call the sudden failure. This is a kind of failure that happens suddenly without any notice. And we have gradual failure, is a failure that has been given signs, showing symptoms before it occurs. So they are categorized into sudden and gradual with respect to the timing. And if we classify the failure with respect to the degree intensity of the fault, we have what we call partial failure, and the partial failure is just a deviation from the normal characteristics. The item will be continuously used, but it is not given the required performance. This is what we call the partial. And the complete failure is the one in which the system has already collapsed. It will no longer be used because it has completely failed. Now, we said we have another classification by combination of the three things we mentioned. That is the causes, the timing, and what the degree. And here we have what we call catastrophic failure. And this is a failure which is sudden with respect to time, and it is complete with respect to the degree. For instance, if you have your fuse and it blows, definitely it will never work again. It happens suddenly and completely. Then we have short circuit failure of capacitors. If a capacitor has a short circuit, it happens suddenly and it will never be used. It's complete failure. Then we have what we call the degradation failure, and these are the failures which are gradual, they give sign, and they are partial. They did not make the machine or item completely useless. And example is change in the value of resistance of a resistor. If you have a resistor that is 10 kilo ohm in value, as you continue to use it, it will be reducing, maybe to change to 7, 6 kilo ohm, like that. You can see it can still give some resistance, but not up to the required value. So we call this one degradation failure. It happens with time and it is partial, it's not complete. So the next thing is the failure rate. We are going to look at it again, but here we are trying to derive a mathematical formula for it. The failure rates, if you can remember, we define it as the number of failures that occur. Here should be failure rate, that is the number of failures that happen per unit time. And we know that this failure rate is an indicator that shows how reliable a system or component is. And the failure rate, mathematically, it is calculated using this formula. Lambda of t is the limit as delta t tends to 0 of 1 over ns times delta nf delta t. And you know, if this delta tends to 0, from our knowledge of calculus limit, this will change to dnf dt. And where this ns is the total number of the item that survived, and delta nf is the number of components that failed within a short time, delta t. Let us give a worked example to illustrate this one further. Out of 1010 items, 10 failed when they were subjected to the test during a period of 5,000 hours. We are now asked to find the failure rate. Now, see from here, I have 1010, 10 failed. So the ones that survived, my NS should be 1000 components. And my delta NF is the number of components that failed, which are 10. And the time during which this failure occurred is 5,000, and I put it here. Evaluating everything, it will give me 2 times 10 raised to power minus 6. And if you wish, you can change these failures to percentage. That is this times 100, which will give me 0.0002% per hour. But one important thing we need to know, we don't express it as percentage per hour. Mostly we express it percentage per 1000 hours. So if we want to change this one from per hour to per 1000 hour, we multiply what we obtain here by 1000, and this will give me 0.2% per 1000 hour. So the percentage failure rate per 1000 hour of some components, as I told you, the failure rate is constant for different components, and the values of some component are given here. That of capacitor, fixed value capacitor, is 0.1% per 1000 hour. For the resistor carbon film type, it it is 0.05, for diode is 0.005, for thermistor is 0.06, and for transformer is 0.03. Now, how do we get these values for different components? These are the basic sources of getting reliable values for this percentage of failure rate per 1000 hours. One method is from the standard part supplier. Those that supply component to people, they will be getting report of those who failed, the component that failed, therefore they can calculate the percentage. The testing agency, we have some laboratories, especially in developed countries, they have private laboratory. Whenever you produce something, you take it for them to test it for you independently. We can get that data from them, and the failure report from users. You as a user, you know how many you bought, how many have failed, you can know what is the failure rate. And the field failure report, that is from those components that are used in actual field of application. And the quality control department, there are some agencies of government, their function is to regulate how things are being done in the country. For instance, NAFDAC in Nigeria, what they do is whatever you want to produce or import as a food or drug, they have to test it in their laboratory to make sure it satisfies the requirements. And there is maintenance and repair reports or records. So this record of maintaining component day in, day out can give you the ability to ascertain what is the percentage of the failure rate. Now we go to another segment which deals with what we call weighting factors. What are these weighting factors? As we know, any component that is used, it can be affected by the effect of mechanical vibration, by the effect of electrical variation, by the effect of temperature variation of the environment, and other parameters like humidity. So for this reason, we bring up what we call weighting factors. That is the amount of effect these things will have on the reliability and the failure rate of the device. We have three of them: the weighting factor for the environment, WE, for the temperature, WT, and for the rating, WR. For the environment here, we mean all other factors in the environment like humidity, like salinity, like pressure, all of them. And temperature is also one of the environmental factors, but it is treated separately because of its importance. And the rating has to do with the amount of current, voltages, frequencies at which we are expected to operate our devices. So if we take these weighting factors into consideration, our original failure rate, which is just lambda, will now change to lambda naught, which is the aggregate taking care of all these components. And here I have my lambda naught equal to lambda times n, where n is the number of the components involved, and these three are my weighting factors: environmental, temperature, and what? The rating. For instance, if I am assessing the reliability of an amplifier, we know in the amplifier, if you open, you can see resistors, you can see capacitors, you can see diodes, and many different components. So we are saying if you want to find the overall failure rate of that amplifier, you get the overall failure rate of resistors, you get that of capacitors, you get that of transistors, you get that of diodes, and you add all of them to give you the overall failure rate of your system. Now, what is the relationship connecting the reliability and the failure rate? Let us assume this NS is the number of components that survives after a test is carried out, and NF is the number of components that have failed. Now we can say the total is equal to N0, which is NS plus what? NF. So my reliability is equal to number of components that survived all over the total number involved in the test. So from this definition, we want to go and derive a formula that will relate the failure rates and the reliability of a system. Let us go back to our definition of the failure rate, which says is 1 over ns times delta or d nf dt. By rearranging this one, I can say this my ns is equal to n0 minus nf, because if we go back to this slide, you can see n0 is the summation of the two. So therefore, ns should be this one minus this. So from here, I rearrange this lambda, I cross multiply delta t to 8, and this 1 over n naught minus nf and multiplied by delta f, meaning I am integrating this one with respect to t. So if you integrate with respect to t and your values from 0 to t, it should give you lambda t. What brings about this minus? I will explain. Come here. Here it is just 1 over this, isn't it? And if you differentiate the denominator with respect to nf, it will give you minus 1 because it has minus in front of it. So because of here we don't have minus, that's why I put minus here and put minus on the other side so that they will balance. And you can remember the logarithmic identity, that's the natural log identity of integration. If the derivative of the denominator is equal to numerator, you take the natural log of what? The denominator. And here are our limit from 0 to nf. So crossing or multiplying both sides by minus, it comes here. After my substitution and simplifying, I finally go to my minus lambda t equal to natural log, that is log to base e of what? N naught minus nf all over n naught. And if you wish, you can further simplify this to this. So let me go back to my definition of what? Reliability, which says is equal to ns all over n naught, and ns is equal to n naught all over minus what? Nf. And you can see whatever I have here. Okay, there is one thing I missed. In trying to remove this natural log, you have to take the exponential of both sides, and this would work. So this one is equal to this, and it is equal to this. So can we see that this one now, it is this, and it's equal to my exponential minus lambda, and this one, which is the same value, is equal to reliability. Therefore my reliability is equal to exponential minus failure rate times t, where t is what? The time. That formula, there are some important things we need to note about it. If the failure rate of the component is not constant as we assume, the formula will now be like this: exponential minus integral of lambda t dt from 0 to t. And if the value of our time is very, very small, we can say the reliability, which is exponential minus lambda t in the previous slide, is equivalent or very approximately equal to 1 minus lambda t. For instance, let us assume our lambda is this 2 times 10 to the power minus 5, and the time for the experiment is only 5 hours. If you substitute directly these two items here, it will give you this. If you substitute here, it will give you the same thing, meaning this and this are approximately equal to one another. We should also note that this value is only close to 1. This 0.999 is not equal to 1, but it is very close to 1, because we said there is no system that will be 100% efficient. And there is another thing we call failure density function. And what is this? It is the derivative of the reliability. That is, if you find the r of t dt and you put minus, whatever you get is your failure density function. So let me go back to my definition or my formula for the reliability. That is, r of t is equal to minus lambda t minus exponential lambda t. If I differentiate this, differentiating exponential, we leave it as it is, and we now differentiate the power, which is minus lambda t. Differentiating with respect to t will give me minus lambda. But in my formula here, I told you 1 minus is already existing, so minus minus should be plus. My failure density function will be lambda exponential minus lambda t. There is another formula we call Poisson distribution. PR equal to lambda t raised to power r all over r factorial exponential minus lambda t. And this formula is the probability for the occurrence of r number of failures in a given time t. Now let us assume we want to find the reliability, that is the probability that 0 failure occur. If 0 failure occur, it means my r is equal to 0. I should put 0 for this, and I should put 0 for this. So here I have lambda t raised to power 0, here I have 0 factorial. Any t raised to power 0 according to law of indices should be 1. 0 factorial is also equal to 1. 1 over 1 should be 1. Therefore, my p naught is equal to exponential minus lambda t. Can you see that this is the formula for my reliability? Yes. Therefore, using this Poisson ratio, we can derive the formula for our reliability. So we are still trying to derive the relationship between parameters of reliability. This time around, we want to derive a formula relating the mean time between failure, the mean time to failure, and the failure rate. We know already that m, which is mean time between failure or mean time to failure, is equal to 1 over what? The failure rate. How do we get that? We are going to show it here. My m is integral of reliability with respect to t from 0 to what? Infinity. Now, what is my reliability? Is exponential minus lambda t. Putting it here, integrating exponential, I leave it as it is, but I will divide by the derivative, which is minus lambda, 1 over lambda. Now, if I substitute my limit from 0 to infinity, you will see that I have something like this. This will be equal to 0 and this will be equal to 1. Simplifying this will give me 1 over lambda. Just to prove that mean time between failure is equal to 1 over failure rate. And it is also called the mean time to failure for the components that are not repairable. So the next item is if our failure happened by chance, that is failure that happens within the real life time of a device or a component, our lambda, as we have just seen, is 1 over mean time to failure, non-repairable, 1 over mean time between failure for the repairable items. And there are some points we need to notice. One of them is that the assumption that this lambda is constant with respect to electronics component is almost always true. Each electronic component has a fixed value of the lambda, the failure rate. So after that, we now go to a method of showing the relationship between the time and the reliability of any system. Remember, my reliability, we have obtained it to be what? Equal to exponential minus lambda t. Now, since here I have minus is the same thing as 1 over exponential lambda t, meaning whenever the value of t increases, the exponential will increase and 1 over the exponential will be decreasing to 0. Meaning my reliability will start from the maximum value, which is 1, and as the time is increasing, it will follow this curve, which is exponential decay. And the reliability of a component will be represented by this letter R, the unreliability of the component by letter Q. So the summation of reliability and unreliability is equal to 1, meaning my unreliability is 1 minus what? The reliability. That is, Q is equal to 1 minus exponential minus lambda t. So if this term is decreasing exponentially, then 1 minus it will be increasing exponentially towards 1. And that is the curve here. It represents the curve my unreliability. As the time increase, the reliability is what? Reducing? Yes. The unreliability will now be what? Increasing. It's the same statement. We can use the same formula to show the curve of the tendency of survival and the tendency of failure of devices with respect to time. Let me go back to my definition, which says R is equal to 1 minus NF all over N naught. And we said this R also is equal to exponential minus lambda t. So if we take LCM here, you have N naught minus NF all over N naught equal to this. Crossing, you say your reliability is now equal to N naught exponential minus lambda t, like this. That is my possibility of what? Survival. NS is equal to N naught exponential minus lambda t from here. Look at it. If you say this, come here, it should be N naught minus NF, and N naught minus NF is definitely equal to NS. So this is my number of survivors is equal to N naught total number exponential minus lambda t. What are we trying to show here? Whenever this time is increasing, our exponential minus lambda t will be decreasing, which means the number of survivors is also reducing. So we are saying as the time is increasing, my survival rate is reducing exponentially, tending to 0. And also we know that from this expression we can find the value of our NF, that is the number of the failure devices and it is equal to n naught into 1 minus exponential minus lambda t. And as we have did in the other case, whenever this exponential minus lambda t is falling exponentially, 1 minus it will be rising, meaning my number of the failure will be increasing. Therefore, this is the curve representing the number of failure when the time increases. So for us to understand what we have done so far, here is a worked example number 5, and it says 1000 identical electrical components, each of them with a failure rate of 5% per 1000 hour. Each are put into test together, all the 1000 components. So we should find the time lag, that's the duration of the time before the following failure of the component occur. That's before 100 failed and before 500 failed. Now the number is 1000, that's my n naught, and the failure rate is set to be 5% per what? 1000 hours, meaning 1 over 100 because of that percentage, then times 1 over 1000 because it is per 1000. Everything gives 5 times 10 raised to power 5, my actual failure rate. Now if I want to find the time for the failure of 100 components, I'll remember my formula, which says the reliability here is equal to 1 minus nf minus over what? N naught, and it is equal to exponential minus lambda t. And that's what I did here. 1 minus number of failed components 100 all over total number of the component, which is 1000, equals to exponential minus lambda, which is found to be 5 times 10 raised to power 5, times t1, which is the time I am asked to evaluate. So looking at this formula from here up to here, the only thing that I don't know is t1. If I evaluate it, it will give me 2107 hours before 100 component failed. And for us to get that of the 500 component related to be t2, substituting in the same expression, I have 1 minus 500 component all over total 1000 equal to exponential minus this times t2, and my t2 is bound to be 13,000 hours 863. So the next thing we are going to see is the failure pattern of an equipment, and this failure pattern, it is drawn in form of a graph, and that graph we call it bat to cup. Why do we call it bat to cup? Look at the shape of the cup. It is just like that container we use in our bathrooms to enter and take bath, and that's why it is called bat to cup. Now looking at this graph, I have 3 regions. This one we call it the early failure period, and this is where we call the useful life period, and you can see it is the longest, and the last one, it is our wear out period, which is on the other hand. Now if you look at the cup here, it is falling down, and here it is somehow flat, and here it is rising up. And how do we get this cup? Is combination of 3 cups. The first one is this. It is representing my early failure rate. If you have a device, the possibility for it to fail when you use it in day 1 is higher than when you go to day 2, is higher than when so as the time is increasing, the tendency of failure at early stage is reducing and falling like this. And the wear out failure, that is the device is becoming older and older, as the time is increasing, the rate of failure in that sense is increasing. And of course, my useful life period, I told you the failure rate is what? Constant, and it is represented by this horizontal dotted line. So combination of this falling line, this rising line, and this horizontal line are combined to give me my bat to curve, which is showing the failure pattern. So the failures occur in how many stages? 3. Early failure, useful lifetime periods failure, and we have what? Wear out periods failure. And what causes them? Let us look at them one after the other. We start looking at the early failure periods, and what are the common causes that cause component to fail at the initial stage we started using it. The first one is manufacturing faults. Whenever you take the design system to the factory where it is manufactured. Whenever there is any fault in the weldings, in the connections, existing of date in a particular region, existing of impurities, cracking or insulation breakage or cutting, all of them, they are termed as what? Manufacturing faults, and they are responsible for the early failure of the components. And we have design fault, and these are the faults associated with mistakes made while designing the system. And also there is another cause, which is the last one, misuse faults. If you buy a system today, let's say a television, and that television is supposed to take 240 volts, but because you have 3 phase coming into your house, you connect face to face to it, it will give you 415 volts, and that is misuse. It will damage it. So manufacturing defect or fault, design fault, and the misuse fault are 3 major causes of what? The early failure period rates. And the second segment, as we have seen in that our graph here, is this flat region, which we call the useful failure period. And what causes failure in that case? In this case, our device is considered to be most useful in that time because it has already escaped the possibility of the early failure. Now it is in its youth stage. Now any failure that occur in this period, it is related to what? Stress. Due to random fluctuations in the voltages in current frequencies, or overstressing the component unknowingly. Therefore, any failure that happen here is due to stress, and we don't have a single reason that we can say it is the cause of this failure in the what? Constant failure period. Then, for us to shed more light on this useful period, many components, many systems, they have expected life duration. For instance, a television is expected to last for 15 years and above. Electric power system, 15 years and above. Television set, 7 to 10 years, based on what? Using 2,000 hours per year. And the air traffic control system that they use in aviations and in airports, they have the life expectancy of more than 15 years. Like solar panels, they have life expectancy of around 25 years, and different components. Now we go to the last segment, which is the wear out period. And this wear out period is a period where the device has already become old, parts of the components have been started fading away, that is wearing out, and this may be as a result of corrosion, as a result of oxidation, as a result of breakdown of insulation, as a result of friction wear, as a result of shrinkage, that is reduction in size, and as a result of fatigue, becoming weaker and weaker. Even a human being, as you grow older, you are experiencing all these setbacks. So if we want to reduce the rate of this wear out failure, all we need to do is to do what we call planned maintenance. That is, before the machine stops working, we stop it ourselves, we replace some part of it and refurbish it so that it will continue to work. So replacement of parts of this machine, refurbishing them, making them as new, will elongate the period before the wear out time arrives. And also in semiconductor devices, this wear out period, sometimes it is not evident, because go to people that repair televisions, radios, take a board that has resistors and other components like capacitors. If you take it even from the dustbin and you remove it, it can work, because they don't experience this kind of wear out problems. So the next thing is the measurement of the mean wear out life of a device. How do we measure it? The first thing, we should put sample of component on test under a condition that is similar to the real life condition until all the components have failed. Now after they all fail, we now bring them out and start examining them physically. We can see the ones that have failed at the beginning of the test, that is what? Early failure. We can see the ones that have taken a long time before they fail. We can say these ones are what? Failure due to wear out. And by that inspection, we can now eliminate the ones that experience early failure and the ones that experience constant failure periods when they are in their useful time. And for instance, if we know that the average lifespan or mean time to failure of a device lifespan is 7,000 hours. So after carrying out the measurement, you found that after 500 hours it failed. Compare it with 7,000. Definitely 5,500 is very much smaller compared to what? The 7,000. And for this reason, we say this one is what? Early failure problem. And after separating the ones that suffered early period failure, constant failure, the ones that suffered the wear out periods, we now measure their time, T1 for the first one, T2 for the second one, up to Tn all over n, which is the number of all the components. To illustrate this, let us take this example, worked example number 6. We are told that we have a sample of identical components with average useful period of 4,500 hours. And this component, they are subjected to accelerated life test. What we mean by accelerated life test? If we want to find the lifespan of a component that we think it is like 1,000 hours, maybe we can test this for only 100 hours and the result can tell us that it can reach 1,000 hours. We are going to discuss it in the second segment of this course. And we are asked to determine the wear out time. So you see, if you look at this column, the average time lifespan of it is this, but it fell in 6,120. This one has this, it fell here. All of them with their normal life and the failure time. Now, if you look at it, we are told that it has average of what? 4,500. So we can say any time we measured between 4,000 and 5,000, we can call it a constant failure period. And anything less than 2,000, we call it early period. But anything that is greater than 5,000 is a wear out period. So now this is greater than 5,000, this is greater than 5,000, this is greater than 5,000. Therefore, they are wear out failure time. But this is very close to the average 4,005. This one is also close, but this one is 7,000 is wear out. This one is less than 5,000, it is normal. This one is 7,000, it is what? Wear out failure. And this is just 180, which is early failure. 6,000 wear out, 47 close to the average, and 6,002 is the what? Wear out period. So I can say this one plus 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 this one, and there's 7 of them. They should be added and the average taken to give me my average wear out failure period of this component. Now the first one you can see is what? T1, T2 up to T7 all over 7. 6,120, 7,500, 6,700, 7,400, 7,650, 6,420, and 6,200. Adding all of them and dividing by 2 give me 6,856 as my average wear out failure period of this component. Ladies and gentlemen, at this segment or at this point, we have come to the first section of part 1 of our lecture, and I advise you to kindly take your time, read, watch this tutorial over and over again. It will help you to understand, and we stop here until we come with the second segment of part 1 of the lecture. Thank you very much.